Hi there! Welcome to General Physics 1. Our lesson for this week is about kinematics. In here, we'll define motion and explore ways of describing it. We'll deal with a practically interesting case of accelerated motion. At the end of the presentation, you will be able to convert a verbal description of a physical situation involving uniform acceleration in one dimension into a mathematical description. Second, recognize whether or not a physical situation involves constant velocity or acceleration, or constant acceleration. And finally, solve for unknown quantities and equations involving one-dimensional uniformly accelerated motion. Several early Greek scientists, notably Aristotle, put forth theories of motion that were useful descriptions but were later proved to be incorrect. Our currently accepted concepts of motion were formulated in large part by Galileo and Isaac Newton. The branch of physics concerned with the study of motion and what produces and affects it is called mechanics. Mechanics is divided into two parts, kinematics and dynamics. Kinematics deals with the description of motion of objects without consideration of what causes the motion, while dynamics analyzes the causes of motion. This lesson covers kinematics and reduces the description of motion to its simplest terms by considering the simple case of motion in a straight line or linear motion, which is motion in one dimension. Now, what is a motion? Motion involves the changing of position. Motion may be described in part by specifying how far something travels in changing position, that is, the distance it travels. Distance refers to how much ground an object has covered during its motion, or simply the total path length traversed in moving from one location or point to another. Distance is a scalar quantity. To find the total distance, just simply add all the distance given. Its SI units are meters and kilometers, while feet, miles, and yards for British units. Displacement refers to how far out of place an object is. Also, it is a vector quantity that points from an object's initial position to its final position, and whose magnitude equals the distance separating the points. To calculate displacement, consider the following equations. If the displacement have the same direction, simply add the vectors to obtain the total displacement. If they're in opposite direction, find the difference between the final and initial positions. If they're at right angle to each other, utilize Pythagorean theorem. Units of displacement are the same with the distance. When something is in motion, its position changes with time. This is called speed. Speed refers to how fast an object is moving. This can be conveyed by using length and time to give the rate at which distance is traveled. Mathematically expressed as speed equals distance over the time of travel. Velocity tells you how fast and in what direction an object is moving. It also refers to the rate at which an object changes its position. It is commonly known as the speed with direction. It is given by the equation velocity equals displacement divided by the time elapsed. We define acceleration as the time rate of change of velocity. Operationally defined as acceleration equals the change in velocity divided by the time taken to make the change, or A equals v sub f minus v sub I divided by t sub f minus t sub I. An object is said to be accelerating when the magnitude of the velocity changes, like when, say, a car either speeds up or slows down, or even comes to a stop when nearing intersecting lanes. When the object's direction changes, such as a rotating top or a merry-go-round ride, or both magnitude and direction changes, when a car overtakes another, or when it turns to left or right lane. The general rule of thumb is if an object is speeding up, the acceleration is positive and it's in the same direction of motion, whereas if an object is slowing down, its acceleration is negative and opposite the direction of motion. For example, Michael is driving his sports car at 30 meters per second when he sees a dog on the road ahead. He slams on the brakes and comes to a stop in 3 seconds. What was the acceleration of Michael's car? The given values are initial velocity equals 30 meters per second, final velocity equals 0, the change in time equals 3 seconds. We find the acceleration. Acceleration is given by the equation final velocity minus initial velocity divided by the time. Substitute the given values to the formula, we will be able to obtain an acceleration equal to 10 meters per second squared. The simplest kind of accelerated motion is straight line motion with constant acceleration. In this case, the velocity changes at the same rate throughout the motion. The description of motion in one dimension with constant acceleration requires only 3 basic equations. These are displacement equals velocity times the time, equation 1. Average velocity equals the sum of final velocity and initial velocity divided by 2, that is equation 2. Acceleration equals final velocity minus initial velocity divided by time, equation 3. The description of motion in some instances requires multiple applications of these equations. These algebraically combined equations are called kinematic equations. Kinematic equations are a set of equations that can be utilized to predict unknown information about an object's motion if other information is known. The equations can be utilized for any motion that can be described as being a constant accelerated motion. When the acceleration is constant, the average acceleration for any time interval is the same. This makes it easy to derive equations for the position and the velocity as functions of time. To find an expression for final velocity at a later time, we replace equation 3 as shown to become final velocity equals initial velocity plus acceleration times the time. This is known as equation 4. Next, we'll derive an equation for the position as a function of time when the acceleration is constant. To do this, we use 2 different expressions for the average velocity during the time interval. The first expression comes from the definition of equations 1 and 2, which is true whether or not the acceleration is constant. Combining the equations involved by substituting for the velocity to give the displacement equals the quantity of v sub f plus v sub I divided by 2 times the time. This is equation 5. Next, we use equation 5 and then substitute for final velocity from equation 4, which gives displacement equals 2 times the initial velocity times the time plus acceleration times the time squared divided by 2. Simplifying gives displacement equals initial velocity times the time plus 1/2 of acceleration times the time squared. This is equation 6. Finally, we set equation 5, then write equation 3 in the form of time equals final velocity minus initial velocity divided by acceleration gives an expression for time that we can substitute into the previous equation, giving displacement equals the quantity of final velocity plus initial velocity divided by 2 times the quantity of final velocity minus initial velocity divided by acceleration. Simplifying gives the final equation: displacement equals the square of final velocity minus the square of initial velocity divided by 2 times the acceleration, or 2 times acceleration times the displacement equals the square of final velocity minus the square of initial velocity. This is known as equation 7. Now, keep in mind that if the object is at rest or stationary, the displacement is constant and both acceleration and velocity are constant. If the object is moving at constant velocity or uniform velocity, the displacement is changing and velocity is constant, while acceleration is 0. If the object is moving at constant acceleration or in uniform accelerated motion, both displacement and acceleration are changing, or the speed is constant but its direction is continuously changing. For example, Albert is riding his scooter at a velocity of 80 kilometers per hour when he sees an old woman crossing the road 45 meters away. He immediately steps hard on the brakes to get the maximum deceleration of 7.50 meters per second squared. How far will he go before stopping? Will he hit the old woman? The given values are initial velocity equals 80 kilometers per hour converted to 22.22 meters per second. Final velocity equals 0 and acceleration equals 7.50 meters per second squared. We find the distance before Albert stops. The equation here is distance equals, or rather displacement equals, square of final velocity minus the square of initial velocity divided by 2 times the acceleration. Substituting the given values to the equation, the obtained distance therefore is equal to 32.9 meters. Since the old woman is 45 meters away, therefore Albert will be able to stop without hitting her. Another example, an object starts from rest with an acceleration of 10 meters per second squared. How far does it go in 0.500 seconds? What is its velocity 0.500 seconds later? Given values are acceleration 10 meters per second squared, time equals 0.500 seconds, initial velocity equals 0. We find the distance and the final velocity. Equations are distance equals the initial velocity times the time plus 1/2 of acceleration times time squared, and for final velocity equals initial velocity plus acceleration times the time. We solve for the distance first. So we substitute the given values to the formula. The obtained distance therefore is equal to 1.25 meters. For letter B, for final velocity, we substitute the given values to the formula of final velocity, and the final velocity therefore is equal to 5 meters per second. These are the references. Thank you for watching and good day.